Hello everyone, welcome to Physics 2211, lab number 3, finding the mass of a black hole. We begin once again with Newton's second law, or the momentum principle, which states that if there is a change in momentum, that means there is a net force acting on the system. Now sometimes the net force is not parallel to the direction of motion, such as in circular motion or in space orbit. And so this is what we're going to look into today. The purpose of this experiment will be to create a computational model of the interactions between a black hole and a star, and also to calculate the mass of a certain black hole created by the seed, which is my GT email. Because this analysis strictly relies on a computational model, the equations will be integral to the analysis. So what equations are there? We utilize the velocity and position update formulas. And using these two, we can derive the momentum update formulas. Also, we know that F net is the change of momentum over the change in time. And we can also utilize the circular motion ones, which breaks up the F net into its perpendicular and parallel forces to motion. Here is how some of these equations show up in the glow script code. We see up top, we have the velocity update formula. Towards the middle, we utilize the momentum principle, where we literally take the change in momentum over the change in time to find the net force. And then towards the bottom, we break it up into the perpendicular and the parallel changes of momentum. Now you might be wondering, what happened to the gravitational force, net force formula? Well, we'll get to that one later. Before this analysis begins, we are also given some very important data. For example, the star's mass is 2 times 10 to the 30th kilograms. And we also know that our time interval will be 1 day, which approximately is about 86,000 seconds. And we also know we will be utilizing G as 6.7 times 10 to the negative 11th. Now looking at the bottom of the screen here, we see actually how the computational model ends up looking like. How it begins with very small forces, and as it gets closer, the force of gravity grows exponentially. So how do we use this model? Well, this is where our good friend, the gravitational force net force formula comes in, where F net is equal to G m1 m2 over the magnitude of the distance squared. And using this, we can solve for the second mass because everything else is calculable. And we get m2 is equal to the net force times the distance squared over G over m. And plugging this into the Python, as seen on the bottom, gives us a mass of about 1.4 times 10 to the 34th kilograms. And that is the mass of our black hole. So, what could have gone better? Well, the one issue I have with what we did here is that there is a lot of rounding and likely a lot of accumulation of error. The GlowScript program calculated a value of the mass at every single time interval. And here is the wide variety of masses that it got as solutions. And this was likely due to the inconsistency of the gravitational constant, either that or any other rounding errors that would have taken in the middle of this, or approximations that would have led to final inaccuracies. Now, here are some interesting things to think about. Are the net force and the parallel and perpendicular components different from the rate of change of momentum in the parallel and perpendicular components? And the answer is actually no. As seen from Newton's second law, F net is delta P over delta T, and that also goes for its components. Now, if we were to switch out the black hole with a new black hole with different mass or something, and the original motion of the star didn't change, would we be able to find that mass? And the answer is no. We would not be able to find that because we wouldn't be able to see it change, and we couldn't be able to calculate anything from that. Ultimately, we just used a computational model to analyze a system that was completely out of this world. See you on the next one.